the real potential and practical applications of AI today, in the near future, and looking ahead. And I think we're going to have a really exciting evening looking at both, the real kind of art of the possible, but also, some really practical grounded examples. And we come on to our panel session of how AI is being implemented in businesses and organizations in lots and lots of sectors. So I'm Chief Operating Officer of TechEast. TechEast, as some of you will know, was created in 2016 really to shine a light on the fantastic and diverse tech business scene and tech economy in the east of England, which is sometimes missed or has been historically on the national and international radar, but no more. We are firmly on the map, and it's particularly important that we bring in expertise and insight from outside the region, and where we have connections to, for example, Andy as alumnus of UEAi, but now having gone out into the wider world and very much into the widest possible world of technology at IBM, to bring ideas and to cross-fertilize with what we know to be a fantastic city and county and region for tech with the wider world. So fulfilling the promise of AI is our theme this evening. We will probably talk about a wider bundle of technologies than simply the wide bundle of technologies that it is artificial intelligence. We'll have some examples around that. But just a few kind of housekeeping things to talk through for the evening. So first, if you have your smartphone with you, please keep it switched on, but on silent. We do have an event hashtag. It's hashtag UEAi. We are going to have a panel after Andy's keynote, and we'll be using the Slido web app. If you have used it before, you'll know how it works, but you can go on your phone, just sli.do, either download the app or just use the web browser, and the tag is hashtag S567, so you can ask questions to the panel. But now I'm delighted to introduce this evening's keynote speaker. Andy Stanford Clark is CTO at IBM UK, and is not only an IBM Distinguished Engineer, but also Master Inventor with more than 40 patents, and, as Gerard said, a UEAi alumnus with a PhD in computer science, and an honorary professor here as well. And I know that over the last couple of days, Andy's been immersing himself or being guided around the fantastic kind of assets that we have here in Norwich and at UEA. So without further ado, please join me in welcoming Andy back to Norwich and to the stage. Thank you.
Wow, it's great to see so many people here. It's a bit worried because we had about 70 people at our event last night, the opening of the doctoral college here at UEA, which was a great evening, but we had a lecture theatre bigger than this and just a few people scattered around. So it's great to see so many people come. Thank you. So I just wanted to really just set the scene for where we are with different facets of AI. And as Tim so eloquently put it, we'll go wider and broader and deeper, and hopefully we'll get some really good questions from the panel and from yourselves later on, because that's really what it's all about. A lot of people have different sort of interpretations of AI, where it's going, different concerns about it. So hopefully I'll kind of set the scene and sort of plant a few little provocative thoughts, and you can ask us about them, grill us about them later on in the Q&A. So sometimes it's okay to stop and just say, wow. And it's very tempting just to sort of go, it's AI stuff, be blasé about it. But so you just go, wow, actually that's rather impressive. This is the caption, a green bird sitting on top of a bowl, for one of the Microsoft photo captioning competitions. It's an annual event, and so they give you a whole lot of photos, and you basically give them to your computer, and you have to come up with captions for them. And it's a very wide range of subjects. And it's a hotly contested competition. It just so happens, no coincidence, that the IBM Watson image processing technology is currently at the top of the list. It won last year's competition, but there's no reason why that should continue, because it really is hotly contested. But when you think about what's actually happening here, I mean, yes, it is a green bird, but it's kind of only half a bird. It's a kind of weird-shaped bird, and the bowl's got sweet corn on it, and there's all water spraying about. And to us, it's pretty obvious, but when you think that all the computer has is a whole load of dots, one after the other, red, green, blue, thousands and thousands and thousands of those, to actually get that sort of interpretation is really quite impressive. And I had to admit, I stopped and said, wow, when I saw that for the first time. So we've come quite a long way in quite a short space of time. I mean, AI has always been the promise of science fiction. But back in 1996, IBM's Deep Blue computer beat Garry Kasparov narrowly at chess. And it's interesting to see how things have progressed since. And that was seen as a breakthrough in AI, that a computer could beat a human at chess. But that was a very specific chess-playing computer. It had chips that were specific to exploring chess moves. If you'd have asked it for the weather forecast, it would have no idea. If you'd asked it to play drafts, a very similar game to chess, even on the same board, it would have no idea. So it really was a very focused, a very specific function. Scroll forward to 8 years ago when IBM's Watson computer beat the two highest scoring winners of the rather strange American panel game Jeopardy, where the question is the answer and the answer is the question. That's all I'm going to say about it. But essentially, it involves having an incredible understanding, in quotes, of the world. We fed it encyclopedias and dictionaries and all of Wikipedia and a whole bunch of things. And it made a whole load of inferences about how facts are related to each other. And then when the questions were asked, it was able to go through and find out which possible phrases and connections were more likely to be the answers than others, ranked them, and if it was above a certain level of confidence, it physically actuated a button, a servo, which pressed the button, which buzzed it in. Meanwhile, the two guys who were they were guys, in fact, who were it was competing against had also had the chance to think about it. If they were fairly sure they're probably going to get the answer, they would buzz in already, because knowing that by the time their name had been called, they'd probably had the chance to actually think of the real answer. So we were at a slight disadvantage with our interface to it. But nonetheless, we actually beat these two high-scoring winners. And the one on the left said, I, for one, welcome our new computer overlords, when he realized that he'd been beaten. That was quite an interesting moment. And so when we kind of won Jeopardy, which was a big publicity stunt, basically, and showed that you could imbibe not the complex, not the chess moves, which are really quite simple to express mathematically and just kind of enumerate them, but this was a whole lot of what we call unstructured data. So it was data like words and phrases and sentences and paragraphs and nuances of meaning, which, rather like the bird in the bowl, it's not obvious how you tell a computer what that means. So when we finished doing that, we decided to make Watson earn its living, because it cost us a large amount of money to get to that point in our research labs. So we let it loose on the problem of assisting cancer doctors in making diagnoses. So the problem with cancer, one of the problems with cancer, is that there are so many academic papers published on cancer each year that even if you spent the whole, 24 hours a day for the whole year reading those papers, you wouldn't keep up. So if your oncologist tells you that she's fully up to date with the latest literature, call her bluff, because she couldn't possibly be, because she wouldn't have time to sleep, eat, or treat patients. So what the Watson system does is it reads in all those papers, it analyzes the unstructured text, makes lots of inferences, and then when the doctor feeds in symptoms and thoughts about diagnoses and tests that have been done, it tries to find correlations in the huge database of text and comes up with some suggestions that, oh, by the way, did you see this report, this study, which suggested this possibility? Or have you tried this test, which in combination with those two tests shows these things? And you might go, ooh, hadn't thought of those, that's interesting. So it's really just, and we use the term augmented intelligence for AI rather than artificial intelligence, because it's really sitting alongside a professional oncologist, helping them in the things that the computer's good at, so that the oncologist can do the things that they're good at. And we quite often see this duality, this humans and machines working together to achieve a better outcome. So how can we do this? Well, three things have changed. One is we've got vast amounts of data now, and we talk about Internet of Things, getting data from sensors. That's been my background for the last 20 years, working in Internet of Things. But it's really, everything's all about the data. And the fact we can store that data, we can structure it better, and we know how to process it, we know how to do image processing, that kind of stuff. That's really helped. The algorithms for machine learning largely go back a long way, and I played around with neural networks when I was a lad back at university here, 30 years ago, and a lot of those things like neural net classifiers and so on are still just as relevant today as they were then. The problem back then was that quite often we'd come across a problem which was just too big to solve, so we couldn't find an optimal solution, because even if we'd run the lovely computers in the computing center flat out for years and years and years, they wouldn't have had a chance to search through all the possibilities in order to come up with the answer. So now we've got algorithms have improved greatly, so we have things like deep learning, where we've got novel algorithms for doing that better, more efficiently, but also we've got access to vast amounts of computing power, both in our data centers and moreover in the cloud. So rather than having to own thousands and thousands of computers to do the machine learning, you can just invoke a set of 1,000 cores, 1,000 processors in the cloud, do your learning for a few hours, tear them down again. So the efficiency of just sort of buying compute by the hour is very much evident in this kind of world. So you can just bring those devices to life when you need them. So that's really what's allowed us to move this stuff ahead. And it has moved a lot. I mean, we've been doing voice recognition for years and years and years, but now you just chat to your Amazon Echo like it's a friend. So I know you have to do questions and answers, so it's a little bit stilted still, but people don't really realize the cleverness of the fact that it understands pretty much speaker independent, accent independent, gender independent, culturally independent. It pretty much always understands you. I know some Glaswegians who will take offense to that, but it does pretty much always understand you. And one thing that's worth saying is that when we talk about AI, actually that's a bit of a catch-all for a broad spectrum of algorithms and data uses, which really are underpinned by it being all about the data. So most of our businesses now, it's the whole sort of industry 4.0 value proposition, which is that our businesses are run by data. We process data to get actionable insights to tell us what we should do next, and use that to make the best decision of how to run our business. We might be doing predictive analytics to predict when a pump is going to fail, or when a patient is going to suffer an injury or something like that, or whatever it is. And so running your business on data is kind of the mantra. And a lot of people refer to that as AI, but actually it's more and less than that. So I tend to think of it as being a spectrum of capabilities from, on this end, very simple statistics, max, min, average. You can tell a lot about things like energy usage in a home from just those simple measures. Then you move a bit along and start moving into the big data science areas where you're doing analytics. And you move into the software modeling area that we term digital twin. So you build a software model of some physical system, and you feed it with data from that physical system so that it becomes a sort of a representative of it, a digital twin of it. And then you can poke about on that model and ask what-if questions and run ensembles of possibilities of possible future outcomes to work out what best to do to optimize the efficiency of the physical system you're talking about. And we're seeing that a lot in smart buildings and automotive and healthcare, where people are building these digital twins of parts of the system to work out what they should do, how best they should treat them. And then moving further to this end, which is the right in my eyes, or left in yours, we start to move into the more complex analytics like linear regressions and multidimensional optimizations and training neural net classifiers and the broad class of machine learning, what's termed artificial intelligence. So as I say, we're on this spectrum of complexity where the computer is using data to predict outcomes. And then you get to the far end of the spectrum where you've got the really sort of human-like reactions, things like image processing, audio, acoustic processing, and video processing, where the computer is actually doing things that are quite similar to what a human could be sitting in front of the screen and doing for you. So one example is we're doing some stuff with Kona, people who make lifts and escalators. They're doing effectively dangling a microphone down the lift shaft and listening to what a lift does when it's operating. And you know when you get in the lift and it goes, or makes a weird crunking and gangling, those are interesting words, aren't they? Sort of strange gurgling noises. You think, I perhaps don't want to be in this lift. Well, that's what the microphone's listening to. and it knows what a proper, a well-behaved lift is sounding like, and as soon as it deviates from that, it raises an alert. It doesn't know what's wrong, it just knows that something's different, and that's enough to call an engineer out to find out what's going on. So that's really adding value and hopefully making sure nobody gets stuck in the lift, which is a very good thing. So remember, it's all about the data. So this idea of augmented intelligence, where we've got humans doing what they're good at and machines doing what they're good at. I mean, clearly machines are good at sifting through large amounts of data, doing heavy-duty computation on things which you could do with a calculator, but it's just boring and repetitive, looking for patterns and having access to a huge catalogue of data which you could hold in your brain, but you'd probably need a sort of USB stick in the back to cover the same number of gigabytes and terabytes that a computer can hold. But if you use that to augment what the humans are good at, the intuition, the common sense, the expertise based on cumulative history of doing this stuff before, and join those things together, then you end up with better decision making. And that's really where we see the future of AI being, not sort of taking away jobs, but really helping people either augmenting their existing jobs or freeing them up from the dull, dirty, and dangerous, the 3D jobs, as the robotic engineers call them, and allowing us to do more challenging, jobs that are more worthy of humans. So we're on this another interesting spectrum of the breadth of the AI. Now, remember I mentioned the Deep Blue computer that beat Garry Kasparov at chess. That could only play chess. Okay, so that's on the far left-hand end. Very narrow AI, focused on a very specific, very good at, but focused on one specific task. As we start moving to the right, and the arrow saying we are here is possibly slightly debatable, but the idea is there's much more to the right of it than there is to the left of it. That's the main point here. So we're in an interesting state now where you've got things like the Amazon Echo, where you can ask it quite a broad range of things, but you have to ask the specific skill. So you say, Alexa, ask the bartender how to make a screwdriver, and it tells you the recipe for making a screwdriver cocktail. If you said, Alexa, ask the weather forecaster how to make a screwdriver, you say, I'm sorry, I don't know how to make a screwdriver. So it only knows the particular domain you've selected. And by asking the skill, you've automatically massively narrowed down the domain you're talking about. And the further we move to the right in there, the less that requirement to be specific about what you're talking about happens. So as we start moving further to the right, you get more like the sort of Star Trek computer, or Holly on Red Dwarf, or the one on Eddie the shipboard computer on Starship Heart of Gold, where you can literally ask it anything, and because it knows who you are, your context, what it's talked to you about before, and its world context, so what it knows about the world around us, you can ask it anything and it can make a sensible response because it knows its situational awareness, it knows what's going on. Now, we're clearly way away from that yet. That's, say, 2050 and beyond might be optimistic or pessimistic, I don't know, but it's stuff's to the right, and we've got an awful lot to do in the structuring of knowledge, the worldview and the context, so that these AIs can actually have be able to pick up the idea of what you're talking about based on what you've talked about it before and what it knows about the world. So we're quite far to the left, despite how magical some of the stuff around us seems today. We're also moving in the directions of sophistication of understanding of sort of human emotions and sort of subtlety of nuance. So we've got the image processing and the signal processing, which we're getting quite good at. It seems quite magical. It's pretty good, but it takes very concrete input and produces outputs. We're now moving into much more sort of some of the more subtleties of language. So we demonstrated a thing called Watson Debater a few months ago, which was a thing which would do the thing where somebody speaks on a subject and then somebody speaks against it, a debate thing. And so it listens audibly to somebody giving the pro side of an argument. Then it sits and thinks about it for a few minutes, getting data from the internet to assemble a counter argument. And then it picks facts from what the argument that was presented, refutes those, and presents its own arguments against the motion. And it actually does a pretty good job of it, surprisingly good. Although the demonstration I saw started picking on sort of personal aspects of what the other person had said, like, you seem to be speaking rather fast. Well, it was just demonstrating the fact that it had counted, it had measured how fast the person was speaking, but it came over quite sort of brusquely. It was a bit insulting. But that's pretty impressive, and that's moving into sort of this nuance of meaning rather than the sort of hard, sort of non-debatable part of it. And as we move to the right again, we get into the idea of what we term affective computing. So the computer can understand our emotions. Imagine it could understand how frustrated you were getting with the fact you couldn't click a particular icon, or the fact you keep typing the same command over and over again, slightly misspelt, but it hasn't worked out that you actually meant DIR or whatever. So these pictures here, we can tell fairly non-controversially what emotion that woman is experiencing or representing. But to have the computer represent that, to recognize that, is pretty tricky. And be able to do it so that it's not debatable is even harder still, so it's non-ambiguous. So that's the direction we're heading in. And this idea of being able to understand subtleties of emotion, sarcasm, for example. I mean, you know, some cultures don't understand sarcasm the same as we do, but computers are completely hopeless at it. So if he says, what did you think of that book? It was really good, meaning it was really rubbish, they would obviously mark it high on the scale of goodness. So it's very difficult to infer sarcasm, things like that. So as we start to move along this spectrum, we start to get better at those things and start to make inroads into that more natural conversation with people, even with all those nuances of language. But we have to be careful. So the problem with AIs, or one of the problems with AIs, is that you can't sort of look through the code and say, right, it's like if this then that, if this then that. Its output is determined by its inputs it's been trained on. Okay, so it's completely so the same code, based on what input it got, can give different outputs. And I can give you a nice example of this. So there's a whole lot of what's called bias in AI, and this is where you either accidentally or not accidentally put in a set of training data which causes the output to be skewed in certain directions. So a good example is if I train a facial recognition system but only give it photos of my friends, okay, people who I know from because I've got photos of them, then necessarily the type of people that, say, let's classify whether people are human or not, let's say, necessarily the judgment that the system will make based on that input will be very much textured by what I've told it. And the problem is that it's very easy to accidentally miss a few people out or put some things in which inadvertently bias the decision in a certain direction. Maybe, for example, it turns out that police stop and search coloured people more often than white people. So they may infer from that, the computer may infer that coloured people commit more crimes. That isn't the case. It's just, unfortunately, from the historical data, that's what it shows up. Now, the problem here is that people tend to trust what the computer says. They say, well, if we put this, say, judgment system or some kind of measurement, some prediction system into a computer and say, right, because we've taken the human out of the loop, it's now a completely fair, unbiased decision, then you've fallen into that trap. And you see it time and time again. There's about 150 different biases that psychologists are aware of, and there's undoubtedly more, and these can be in nuanced combinations. There's a little example you can try yourself on your phone. If you go to Google Translate and do English to Turkish, she is a doctor, sentence, he is a nurse, both perfectly reasonable things to say. That comes out in Turkish as O bir doktor, O bir hemşire, no problem there. Copy and paste that and do it back the other way, so Turkish to English, you get he is a doctor, she is a nurse. Oops, what happened there? So it turns out that Turkish doesn't have gender-specific pronouns like we do, like she and he, representing male and female. So when it comes to do the Turkish to English, which does have gender-specific pronouns, it has to make something up. So doctor, obviously it's a bloke, so it must be a he. Nurse, obviously women's job, it must be a she. Oops, and that's now they could have put they, but that's slightly ambiguous as well, because that was also singular and plural in English, so that isn't non-controvertible. So clearly somebody putting this data in had to put an answer in somewhere, and probably just, oh, well, he and she, probably just a flash, it didn't even pass through their head, they probably just typed something in. But that bias has been caught up in this example. Very interesting. And that's just one little tiny example. You see it all over the place, and they're often much more subtle than that. This one's not very subtle. This is Norman the Psychopath Ai. This is a project that MIT did a few months ago just to prove this whole point of bias. They took an AI algorithm that does image recognition, the labeling thing, like the bird in the bowl thing, and they fed it, first of all, a nice data set, okay, some nice pictures. And then they took exactly the same program, but fed it some nasty pictures into the back end of Reddit and found some really nasty pictures. And they trained up the AI on those ones. And so they now got the same application, same program with two different training sets. And they, as a test, they used the Rorschach ink blot tests, which psychologists use for trying to diagnose psychopath tendencies in customers. So, what do you reckon? What's that? There's no right answer, but what do you reckon? 2 cats, yep. Anything else? Two bears on a mountain, yep, very good. Anything else? So when they gave it to the nice AI, it reckoned, remember there's no right answer, no wrong answer, it's just perception. There's a person holding an umbrella in the air. Okay, that's fine. When they gave it to Norman, the Psychopath AI, it said, man who's shot dead in front of his screaming wife. Oops. And it's worth Googling this, because there are 17 of them in the set, and they're all as dramatic and disturbing as that. So it's really interesting. Same program, just 2 different data sets, showing the bias in AI very spectacularly. So to try and address that, IBM and some other companies have introduced some technology called OpenScale AI, which essentially puts a wrapper around your AI, and it monitors all the inputs and all the outputs, and it builds frequency distributions of the kind of inputs you gave it and the kind of outputs it gave. And after a period of running, it shows up sort of like the statistical histograms, and you actually see where there's any biases starting to emerge. And you can use that then to effectively rejig the input data to change the bias, and you can bias it back again. And you can actually put in a system which is an AI around an AI, which it kind of corrects the biases. I'm a little bit suspicious of whether that's a good idea or not, because you should then run that through OpenScale AI to test whether that thing has any biases, and so on, turtles all the way down. So, but we are starting to address this problem of biases in AI, and the first step is awareness of it. Second step is to monitor it and see how bad it is. So that's what the OpenScale AI stuff does. Really interesting. So where's it going next? Well, I was going to talk about the hardware side of it, because the algorithms will continue to develop, the data will continue to develop, but how are we going to... Often these things depend on massive compute power to run the huge training sets to train up the AI. So there's a couple of directions things are going. One is to scale what we've got already, and we'll already be familiar with things like GPUs, graphical processing units, FPGAs, field programmable gate arrays. So essentially hardware that's dedicated to the task of doing some part of the computation of an AI problem. So that's going to continue. And we sell some really big boxes now with a massive number of cores and a whole load of GPUs connected inside it. Really, really excellent stuff. We then move to an interesting area of sort of brain-inspired technology. This is where we've taken the idea of the neural network, the idea of a synapse with lots of interconnections, and physically embody that in a chip. So we've got this chip from IBM called the True North chip, which has 4,000 cores, 25 million interconnections, and you can train it like a neural network. But then it becomes a physical hardware embodiment of that neural network. The cool thing about that one is it only uses a tiny, tiny amount of energy, so it's a very energy efficient way. Once it's been trained, you can then put it into production. And for things like image processing and gesture processing, it's a very efficient way of doing that. And the third way, and I've kind of taken a bit of a liberty here, of introducing the notion of quantum computing, but we think, so quantum computers, how are we doing time, by the way, Katie? Perfect. Quantum computers are sort of the new computing hardware of the future, and they rely on the fact that the bits that we recognize today are 0 or 1. Quantum bits, or qubits, can be 0 or 1, or all points in between. They depend on this idea of superposed state, a bit like Schrödinger's cat, you know, don't know if it's alive or dead until you look, that kind of thing. And you can actually do computation on a superposed quantum bit. If this doesn't make any sense to you, that's fine. Because Richard Feynman said, if you think you understand quantum physics, you obviously haven't looked hard enough. So don't be disturbed by that. But quantum computers are very interesting, and they've started to become real. So they've been theoretical. So 15 years ago, I went to a talk by IBM's researchers, and they talked about a mathematical model of a future theoretical quantum computer. We now have some actual quantum computers. They're accessible via the cloud, so you can get an account on the IBM cloud and access the quantum computer through a Python programming language called Qiskit, 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 which essentially lets you write a quantum program, and then you put it into a batch queue, and it runs on one of the real quantum computers in New York, which is pretty cool, actually. I did my Hello World on the quantum computer on the 1st of October. It was nearly as exciting as my first Hello World on a BBC Micro 25, 30 years ago. It was quite a sort of life-changing moment. I did a quantum coin flip. So I took a single qubit, put it into superposed state, so it was 0 and 1. Then I forced it into a classical state by looking at it in the computer program, to force it to be 0 or 1, and then it printed out the answer, which in fact was 1, which was heads. So that was the answer to the question. Quantum computers are still not really reasonable to put in your pocket. But then think about what a computer was 50 years ago. You know, it was a room this size for a computer, so you know we shouldn't be too put off by that. This white tube is called the Cryo Stat. This allows the bottom bit, the shiny, the bit where the quantum chips are, to be held at 15 millikelvin, 15,000th of a degree above absolute zero. Colder than most places in the universe. It's jolly cold. Don't stick your tongue on it because it will stick. So it has to be kept there because any little thermal imbalance will tip the whole thing over, and it just won't quantum. The other problem with quantum computers is that they have a very short coherence window, which is essentially like batch windows in old-fashioned computing. You've got about 100 microseconds to get all your computing done. So you haven't got much time before it falls over, decoheres, and you've got to start again. So those batch windows are quite small. So we've currently got a 5-qubit quantum computer. We've got a 20-qubit one available as well. People are building more and more qubits. We think to run anything reasonable, you're going to need tens of thousands of qubits. So we're way, way back in it. But you can start to run little simple algorithms. So it's quite fun. And we think one of the problems, they're very good at solving exponential search spaces, and therefore the learning algorithms for AI are likely to be something that's helped massively by having a quantum computer. I'm now out of time. So, that's our new commercial quantum computer. I was just go, ooh, that's pretty, isn't it? Ooh. So it's a 9-foot cube. Okay, so it's not actually a room-sized one anymore. It's a 9-foot cube. That's the IBM Q System 1. It's like a concept car for our commercial quantum computer that will become available at some point soon. Thank you very much.